Okay, so my presentation is about cache timing attacks. Mostly, how do they work? Description: what is cache? I'll show demo and current results. Mm, Current results in testing in CROSSCON hypervisor. I am. My name is Michał Iwanicki. I'm Junior Embedded Systems Engineer at 3M Agenda. So I will explain what is cache. Shortly explain what is cache, why do we use it, how do cache timing attacks work, some simple attacks implementations, how can they be done, uh, explain how those timing attacks would will work in CROSSCON hypervisor, and show short short demo with current state of the test in CROSSCON. Cache. So what is cache? To put it simply, it's small and fast memory used to store frequently accessed data or instructions or data or instructions that will be used soon. So we don't have to fetch it from RAM but from the faster memory. Well, it is much faster to access data from cache than it is from RAM. Mm, it is much smaller than RAM, pricier, more expensive, at least per megabyte. Okay, well, that's it. Some important concepts, some important cache concepts. Cache level, there can be multiple caches. Uh, each next level, each next cache is usually bigger and slower. There's an image how cache could look. This is generated via LSTOPO from my system, uh, at least part of it, so it would fit. Usually the lower levels, L1, sometimes L2 cache is per core. The the higher level caches are usually shared, or last level cache LLC is usually shared between all cores. Cache hit and cache miss, those are important concepts when we want to fetch get access to some data and it is in cache, then we have cache hit, this much faster access. Cache miss is when we can't, there isn't this data we want to access in cache, and we have to, for example, fetch it from RAM. There's a cache line or cache block sometimes. This is I think I would say smallest if you fetch something from RAM, it is fetched into cache line. The whole block. Usually, it's I'm sure 32, 64 bytes. That depends. So we can't put into cache just 1, 2, or 8 bytes, but we fetch whole cache lines. Cache set, it will be used later. It will be also explained a little more later. Cache contains some number of sets. Those could be tough as the size, the array size. Set set can contain one or more cache lines. That depends on the type of cache. Cache addressing. It, to address cache addressing, if you want to fetch some address from memory, the address is split into 3 parts: tag, index, offset. Index is indexing our set. Offset it's a data offset inside cache line. Tag is memory identifier that we check if the tag is in set. If it is, then that's our data. If it isn't, then it isn't. The address the address used depends. It can be there are 4 possible addressing schemes, a different combinations of physical virtual addresses for index or tag. But usually last level caches use physical addressing for indices and tags. Below is okay. Below is example. Something's wrong. Below is possible implementation of cache in Python. Some simple implementation. Cache is an array or list containing 2 sets. Each set contains 4 cache lines, and cache line contains tag and data. To check if something is in cache, we check if the tag is if the set contains tag. If it is, then we can use that data. We have cache hit. In the other case, we have cache miss. A little lower level, more complete look at cache implementation. There is also additional bit, valid or sometimes dirty, to inform us if we can use if we can use the data from this cache line. If it is valid, then we have to fetch it from RAM. Okay, cache timing attacks. It's a type of side channel attack. This attack type is based on extra information. Side channel attacks might depend on power consumption, timing. In this case, it works by manipulating cache directly or indirectly, and timing, for example, memory access time or program execution time. Those attacks have different granularity or resolution. You can gain information from with precision up to cache line, or less precise attacks can give you information about used cache set. Some attack types that I tried to implement. Some I implemented proof of concept on normal OS, some on hypervisor. Flash and reload. I would say that's easiest of the attacks described here. It consists of 2 parts: flashing or evicting shared memory from the cache, and reloading that memory, so accessing it and timing how much it took. If access memory, if reload time shows us that it was cache miss, then we have to access it from RAM, and that means that no one else access it between flashing and reloading. Cache hit means opposite, that someone access this memory, this cache line between flush and reload, and in that way we gain information that this was accessed. This attack depends on shared memory, works with cache line granularity. It works with shared memory, so we know exactly which cache line, which, for example, 64 bytes were accessed. So it gives us quite a lot of information. Can give us. Another attack, evict plus time, is very similar to previous one. but this time we, instead of timing reload time of evicted memory, we time execution time of program or process. For example, how long it took to encrypt something without when the data is in cache and after evicting it. That way we can find out if it was accessed or not. Mm, yeah, well, that. Uh, and third attack is prime and probe. This attack doesn't require shared memory. It involves two steps, as it's named, prime. The prime step in the prime step we fill cache lines with our own data. So we, well, to put it simply, we, for example, read a lot of data, our own data, to make sure it's in cache, and then probe. We reload that data and time it to find if someone else accessed another memory which was put in cache and as a result evicted our data. So if it's reload data, if it's cache memory that maps, if it's cache miss, okay. The mistake. This should be cache miss. When we probe if it's cache miss, then someone access uh, another memory that maps to this cache set. The biggest challenge with this type of attack is mapping the addresses to cache sets. Mm, attacker needs to know which addresses are used by victim process. So if it's in the same OS, it's maybe not that bad. With sudo, you can map virtual addresses to physical, but between VMs, the practical attack could be much harder. And this attack allows us to detect which set was used, and as there's many addresses that map to the same set, so it it isn't a very precise attack unless you you know or you can guess which addresses are used by the victim. Tests. At first I made two proof of concepts tested on x86 and ARM v8 RPI4 on normal OSs with two programs. Victim and an attacker both used shared library. This shared library just had accessed some internal array, which was also in shared memory. An attacker tried to find out which cache lines were accessed by victim. Though flush and reload and evict plus time worked on x86, flush and reload had some problems on RPI4, most likely due to less precise timing. On x86, I could use directly use register counter to get time. On RPI4, I didn't have that access. I had to use perf interface. Evict and time worked. You the attack. Well, you will see later, but the attack usually shows that the function that we are running around 100 to 150 units longer. That was likely CPU cycles. CROSSCON hypervisor. Main goal of those tests will be verifying whether cache coloring implementation in the CROSSCON hypervisor something. Okay. Whether the cache coloring implementation in the CROSSCON hypervisor prevents inter-VM cache attacks. Well, cache coloring, in short, it's cache partitioning scheme where each VM can only use its own part of the cache. Attacks requiring shared memory will use CROSSCON hypervisor shared memory. The test will use IPC shmem driver. to memory map this this shared memory to memory map and access it directly. This is short description of average plus time implementation, how the test is done, and how demo will show it. We are opening and memory mapping dev CROSSCON hyp C0 created by the driver. First VM victim will calculate median time it takes to finish some function which accesses different parts of this memory, different cache lines. And it will then run in infinite loop and show the difference from the previously calculated median time. If it didn't change, it should be around the same 0 or maybe 30, and won't jump too much. For simplicity's sake, victim program will time itself, as this will test more cache coloring, not different no, not different ways to stop timing programs in different VMs. Second VM attacker will continuously evict requested cache lines. Without cache coloring, there should be noticeable jump in the first VM when we are evicting cache lines used by victim, and no difference when we do nothing or we evict different cache line, for example, 64 bytes later, address that's a little later. Okay, every time test on two VMs. Okay, so I'll show short demo with the current state. There was a question. Oh, no, Daniel is writing something. Share screen. Okay. I will share screen with Tmax. Share. Oh, okay. I have CROSSCON hypervisor started on Raspberry Pi 4 with two Linux VMs, VM1 and VM2. Well, currently cache test works by just a second. Okay, cache test. Okay. First we are timing how much, calculating median time it took to access shared memory, and continuously report the difference. It's around 20, and it won't change. In second VM, we can evict this cache line, and it jumps to around 115. So almost so it median time takes to access memory, or in this case, the time it takes to finish function, which accesses memory and calculates XOR of each value that's accessed, jumps around 100, I think, CPU cycles. We can evict another line that's 64th byte from the beginning of shared memory. In this case, the median time doesn't change, just to make sure it's not a fluke or some other reason the time jumped. This is without cache coloring, and as of now, I tried to enable cache coloring, at least with shared memory, and the results didn't change. So let's go back to slides. Firefox slide. So that's the next steps. Enable cache enable cache cloning and test it. I already did quick test, but I will probably have to retest it again, and add another test that tests if cache cloning works for non-shared memory, as this test works only with shared memory. Those are main next steps with these references. blog post will be out soon. Some references are used for this presentation and blog post, and took some images also from some of those. Questions?
Okay, thank you, Michał. Okay, any questions? I see some comments here.
It's from Daniel.
It could protect from cold boot attacks if we make sure that we know what will be booted. We know what will be booted. That is, the secure boot is on up to kernel and RAM. I guess this is part of the discussion of the
Exactly.
RAM wipe.
Exactly.
Okay. Yeah, I guess that parts of that could go to the last segment, especially the AI part. Any others? Any questions? Okay, so I guess that's it. When we start the next thought in 3 minutes.
I think Aaron needs some explanation, maybe.
Okay. What explanation?
Just I see a question.
Okay, yeah, okay, sorry. I was mainly curious about how an attacker application would measure the time in the cache timing attacks test. Yeah, that's good, good problem. It makes sense how the victim can test itself. Just unsure how the attacker would do that, but I guess that's the that will be implementation dependent. Yeah,
Yes, real attacks, practical attacks, well, might depend on, for example, that application sends somewhere, sends timings somewhere, and you can access that. But I'm sure maybe you could start some kind of process between VMs. And wait for it to finish and time it like that. It really depends on the implementation. Yes, for the simplicity's sake, I timed it in the in the victim itself, so I didn't have to implement some kind of communication. At least in this case. In the other cases, you measure access time to memory, so the victim just has to run. And after that, you attacker doesn't have to know anything about it. Just in this one attack, evict plus evict and time, you have to time the victim itself, the program, the function.
Mhm. I guess the point is that we really care about checking the implementation, and this is not something like you can have like a system runtime protection against cache attacks. Yeah, because then if really someone take control over your system, then they could just fake your time, and then you have no means of good measurement. Yeah, am I correct, or this is like some wrong conclusion?
Could you repeat, because there was some I didn't hear the last part.
Yeah, I'm just like asking if this is correct assumption. If this is more like testing the implementation instead of using that methodology as a runtime protection against the cache attacks.
Yeah, yes, because there are multiple different. Each attack depends. There isn't some. I don't think there is some generic attack. Each attack is implemented based on what we want to know. For example, for AS library, so different attacks would be probably very implementation dependent. For example, how to time it, what information we access, if it's important information or it doesn't matter.